Hello, ladies and gentlemen. My name is Leah Elan, and my project was on the effect of amorphous carbon on hydrogen fuel storage cells. So, as we have all heard from the news in the past few years, global warming is on the rise. Ever since the Industrial Revolutions, the amount of carbon dioxide in the atmosphere has skyrocketed significantly, as shown on this graph. The burning of fossil fuels for energy has been associated with climate change. This has led to serious environmental effects, such as the melting ice caps, catastrophic storms, and global warming. This has created the incentive to move away from fossil fuels and move towards renewable resources. Now, we currently have a multitude of renewable resources to choose from. Now, the problem is that each type has their own disadvantages, which would make them pretty unsuitable for mass use. However, there is one candidate that seems to be a terrific choice for this dilemma, and this candidate is hydrogen fuel. Now, why hydrogen fuel? Well, hydrogen fuel is environmentally friendly and can be used to power pretty much anything. It is easily made, and there is no way we'd run out of it because hydrogen is the most abundant element in the universe, after all. So, with all these positive benefits to using hydrogen fuel, why don't we use it already? Well, here's the disadvantage to hydrogen fuel it's that it is very reactive. Hydrogen fuel is not safe because it is a very reactive element. Hydrogen is the smallest element with having only one proton and one electron. This means that hydrogen bonds react very easily with other elements. These hydrogen fuel primarily consist of H2, which means that it is a hydrogen atom bonded with another hydrogen atom. These bonds can be broken through increasing the energy given to them, such as a spark. Once the spark happens, the bonds will break and the hydrogen will bond to any atom or molecule that is nearby. This will primarily be oxygen or carbon dioxide because of how prevalent those molecules are in the atmosphere. If a spark were to happen when these reactants are nearby, a combustion reaction will occur. A combustion reaction will always create dihydrogen monoxide, or water, carbon dioxide, and a burst of energy, which is generally an explosion. This means that hydrogen fuel is not ideal for a public setting where people could be hurt. Now, there have been studies that have shown the addition of certain carbon substance to hydrogen fuel storage cells have been able to make hydrogen fuel safer. An example of this is carbon nanotubes. Carbon nanotubes work because of their small size. Their small size makes it an advanced semiconductor material. It's a material that can affect the properties of other atoms through their electrons. So far, these studies have been with carbon nanotubes and amorphous carbon created from high synthetic processes. So why don't we use these materials to make hydrogen fuel safe for the public? Well, these materials are very expensive to make, which would make them pretty inefficient for public use. So I decided to find a carbon that would be relatively cheap and would lower the cost. And the carbon that I chose was amorphous carbon created from sugar and sulfuric acid. My hypothesis is that the amorphous carbon created from sugar and sulfuric acid will increase the safety of hydrogen in the hydrogen fuel storage cell because it would have similar properties to the carbon nanotubes and amorphous carbon made from high synthetic processes that have proven to make hydrogen fuel storage cells safer. So, how does this reaction work? Well, you take some granulated sugar, in my case 50 grams, and mix it with concentrated sulfuric acid, 50 milliliters in my case. The sulfuric acid dries out the sugar, taking away the hydrogen and the oxygen from it, leaving only the amorphous carbon. After the amorphous carbon is washed off and dried in case if there's any excess sulfuric acid, the reaction looks like that, and this is what I got out of it, and it looks like this. For this experiment, I made two custom hydrogen fuel storage cells. These are composed of a PVC tubing, a PVC T-piece, a pressure gauge, more PVC tubing, a needle valve, a PVC cap, and an end connector on opposite ends. One of the fuel storage cells has an amorphous carbon substance in it, while the other acted as the control group by not having any. And this is what it looked like at the end. For this experiment, there are two types of tests, the leak test and the delivery to fuel cell test. The leak test determines how effective the amorphous carbon is at storing the hydrogen fuel. Less amount of pressure released means that it is more effective. Each hydrogen fuel storage cell is going to be filled or has been filled with 20 psi pressure per square inch of hydrogen fuel. And over the course of a few minutes, the amount of pressure of the hydrogen fuel cells are monitored and recorded. This test shows how well the amorphous carbon maintains the pressure of the hydrogen fuel storage cell compared to the hydrogen fuel storage cell that does not have the amorphous carbon. This test is important because it shows how well the amorphous carbon can keep the hydrogen fuel from leaking out of the hydrogen fuel storage cell.
If hydrogen fuel is leaking out, then the amorphous carbon is not making the hydrogen fuel storage cells safer, since the leaked out oxygen, or not oxygen, but hydrogen can come in contact with a spark when it is outside of the hydrogen fuel cell and combust. The delivery fuel cell test determines if the amorphous carbon affects the effectiveness of the hydrogen fuel. Both hydrogen fuel storage cells will be plugged into a PEM transparent reversible fuel cell, not simultaneously, and this will show whether or not the carbon inside the hydrogen storage cell affects the hydrogen when it comes to delivering energy. So the results of the leak test are shown here. The hydrogen fuel cell with the amorphous carbon showed a significant increase of leakage than the hydrogen fuel cell with the amorphous carbon. The fuel cell with the amorphous carbon declined at a rate of 0.0405 psi, while the second fuel cell without the amorphous carbon declined at a rate of 1.2 psi per second. This created a safety increase of almost 3,000%, which is amazing. The results for the hydrogen fuel cell delivery test have not been found yet, however, but it is expected that the hydrogen fuel cell and the amorphous carbon will do well on this test. The hypothetical results are shown here. The data in the leak test showed that the storage cell with the amorphous carbon declined significantly less than the storage cell without the amorphous carbon. It showed a significant difference in pressure leakage between the two hydrogen fuel storage cell containers, which showed that the amorphous carbon does increase the safety of hydrogen fuel storage units. Although the data for the hydrogen fuel storage, the fuel cell delivery test has not been found of the hydrogen fuel storage units. The data does support the hypothesis and shows that the hydrogen fuel cell with the amorphous carbon created from sugar and sulfuric acid does make hydrogen fuel cell storage safer. Because the second test was not conducted, the amorphous carbon may not be able to affect the hydrogen's capacity to fuel a fuel cell, which would nullify any use of the amorphous carbon created from sugar and sulfuric acid. Furthermore, 3 trials were conducted for the hydrogen leak test. More trials would have helped solidify that amorphous carbon was the factor that ensured that hydrogen fuel did not leak as fast. Another factor could have been the construction of the hydrogen fuel storage cell for the project. There could have been a human error that would have caused more holes or leaks in one storage cell than the other. However, now that we know that amorphous carbon created from sugar and sulfuric acid has made hydrogen fuel storage cells safer, it is likely that it could be used to help in the future to help implement hydrogen fuel storage cells into modern society. Thank you.